Good morning all. Welcome to the PACE seminar today. The presenter today is Mr. James Fletcher. James joined the PACE research group when he was in his final year of undergraduate degree program. He did a project sponsored by Western Power. Western Power was very happy with the work that he did in his final year thesis. They continued to support him during his PhD studies. And the work he's done so far, he's developed a software tool and to optimize the electric network, which is managed by Western Power. And today he will be talking about some of the work that he has done towards his PhD degree program. Over to you, James.
Thank you, Tyrone. Okay, so as Tyrone said, my project will be on the optimal planning of power distribution networks in rural areas. My supervisors for this project are Professors Tyrone Fernando, Herbert Yu, and Mark Reynolds from Computer Science. My mentor from Western Power is Shervin Fani. So before I really get into the details of the projects that I've been undertaking, I'm just going to go through a base outline of what power distribution network planning involves. So what are the problems that we are trying to address? What's the complexity of the problems? And what are some of the consequential approaches and constraints that we need to model? We'll then go into looking at two applications. One is in traditional network planning and the other in microgrid planning. And for each of these different approaches, we'll look at the motivations, the objectives behind them, some of the methodologies that we have trialed, and the constraints that we've modeled, as well as some results when applied to real networks, as well as future work which we're presently undertaking. Okay, so the power distribution network, for those who aren't aware, in a traditional sense consists of three main sections. It consists of generation, transmission and distribution, and retail, where the generation can be considered to be a centralized or large coal-fired power stations in general. The electricity is then increased at a high voltage and transmitted and distributed to the customers at the retail side of things. So we are focused on the transmission and distribution, or more specifically just the distribution. Now in Western Australia, the generation is primarily undertaken by Synergy as well as the retail. It's not entirely by Synergy, but the vast majority is undertaken by Synergy. The transmission and distribution, on the other hand, at least in the southwest of Western Australia, is undertaken by Western Power. Elsewhere, all three aspects of the power system model is undertaken by Horizon Power. Now, when we're looking at the optimal planning of power distribution networks, our goal is to try and minimize the cost of constructing and operating the traditional power network according to a set of technical and operational constraints. So what this means is that the costs are the capital costs and the operational costs. So you can consider the capital costs to be your physical network assets that you will be replacing, and your operational costs would be composed of the power losses in the line, as well as the energy not served due to power outages. The constraints, while they can be quite numerous, in general they are based on a certain voltage constraint. You need to have an adequate voltage being supplied to a customer, as well as radiality constraints and some other general power system laws, such as your standard KCL and KVL throughout the network. Now, in the bottom right, we have an example of a rural network that we will be considering. In the center of that network, you can see there is a substation. And from that substation, all the feeders, all the medium voltage distribution network is expanding from there. It then expands from that of those feeders to the customers. So when we are considering the problem itself and trying to understand the complexity of the problem, we can consider it to be composed of a set of nodes and edges, where our nodes are our load points, or the customers themselves, and the edges are the poles and wires, essentially. So if you imagine a rural area, when you're driving along the road, you'll have a set of poles and wires essentially parallel to that road. That is the edges we're referring to. Additionally, we'll also have a radiality constraint, because in rural areas, the networks are typically composed in a radial fashion for the purposes of minimizing costs already. So this problem is considered NP-hard, as it's similar to other NP-hard problems, such as the traveling salesman problem and the Steiner tree problem, where NP just refers to non-deterministic polynomial time algorithms. And these algorithms just, what this means is that a solution cannot be found within or by a deterministic algorithm, or it's unknown that their solution cannot be found. So what this results in is that the time taken to solve these problems using a deterministic algorithm can be exponential or potentially even worse. So just to give you an idea of how slow that would be and how many steps you would need to run through of an algorithm, if you tried to do a brute force approach for this sort of problem, by the 15th node, you would have already run into over 1 trillion steps. So if you're already at 1 trillion steps by the 15th node, you can see very quickly, if you add in a few more nodes and a few more customers until you get to the size of a power network, it will quickly run into a situation which you just cannot solve. So these problems, while they are solvable for small situations, they aren't solvable by deterministic algorithms for large cases. So when we're looking at the methods in which we can actually optimize these power networks, as I just mentioned, you have deterministic methods such as the mixed integer linear programming and nonlinear programming methods, as well as dynamic programming. However, we also have heuristic methods, such as the simulated annealing, ant colony systems, swarm intelligence, and genetic algorithms. This is in no way a complete list of the possible heuristics that have been used. This is just the most common ones. Now, the differences between the deterministic and the heuristic methods are that the deterministic methods, they will find the exact solution. However, they're only applicable to small problems or small to medium-sized problems. Whereas heuristics will find a near optimal solution, so not necessarily the very best, but something that is accepted. And they can be applied from all the way from small problems to very large problems, such as what we have in a power network. Now, the applications that we are focusing on will be for the Western Power's rural network. So if you're unaware, Western Power they construct, maintain and operate the Southwest Interconnected System, which is what you see indicated by the blue lines on the figure on the left. Now the Swiss supplies electricity through over 100,000 kilometers of its physical network to over 1 million customers. So it represents a very large investment, very, very large investment. Additionally, in rural areas in particular, a lot of the infrastructure is actually aging. So it was originally established in the 1970s, roughly. And since then, some parts of the network have been replaced, of course, and maintenance has occurred, but there are still large sections of the network in rural areas which are nearing the end of their design life. So they will be needing to be replaced in the near future before they fail. In addition to that, the network over the past 40 or so years has continued to increase in size. That is, customers have continued to connect to the network beyond the original construction of the network in the 1970s and 80s. So what this means is that the people who designed the network to begin with couldn't possibly consider the future connections, the future customers in which they would have had to connect. So based on these constraints, based on the fact that we have a very high cost of infrastructure, we have the infrastructure is aging, and we have the fact that a lot of the customers have been added to the network over time, we want to consider, is rebuilding the existing network the best possible option, or can we do better? Can we optimize based on the fact that we have this information, whereas the people who originally designed the network wouldn't have had that information? So we've applied two different methods about going and solving this problem. The first looks at rerouting the network topology. So we're saying physically, if we connect two customers via a different route, is that a more optimal solution? And we're using a genetic algorithm to do this. The second method looks at standalone power systems, which are supplying power to customers at their point of demand rather than from the centralized generation source, which is the traditional network model. And to do the second approach, we've developed a network tracing algorithm to find viable candidates. So just provide a brief background into standalone power systems before we get into the actual applications. A standalone power system is an off-grid power supply which supplies power to the customer at the point of demand, as opposed to from a centralized source. So normally, what you consider the power system model to be is a centralized generator, a very large generator, transmits and distributes electricity over a long network until it gets to the customer and a retailer takes over for the metering. In this scenario with the standalone power system, the generation, transmission and distribution, and retailers all in that one location. In fact, you likely wouldn't have transmission and distribution, you would have just some small LV network. Now, the standalone power systems, at least in Western Australia, are typically solar and wind based, so they're renewable based, and they usually have a non-renewable backup, such as diesel generator. Of course, since we are using renewables, battery banks are often used to store the excess energy from solar and wind. And here's just an example of a standalone power system that is being trialled by Western Power. So the network routing algorithm itself, the genetic algorithm. What is a genetic algorithm? It is an optimization meta-heuristic which mimics the evolutionary process through a set of genetic operators. So you can think of this as natural selection, essentially. So we start with a population of possible solutions where the different colors indicate different fitness values. Higher fitness means more likely to survive. We then select which individuals are going to survive or mate to the next population, which are the higher, more likely to be the higher fitness individuals. And then these fit individuals will then breed and produce a new population of higher fitness. That's the general outline of how the GA works. The reason we chose the GA for this particular application is because of its ability to optimize complex combinatorial problems, which is precisely what the power network issue or planning issue is. And of course, it's been applied in the literature. So it's been shown to be effective in other applications quite similar to our application here. So the way in which our genetic algorithm actually works, we define our objective function based on a set of capital costs, operational costs, and penalty costs, where the capital costs are, as referred to earlier, are the physical assets themselves, so the poles and wires. The operational costs consist of the power losses in the line. So you consider this to be your thermal losses due to the electricity passing through your wires. And then lastly, the penalty costs just refers to not meeting certain constraints. So if you aren't meeting the voltage constraint, for example, you would incur a penalty to the system. And equations 2 to 5 just represent how we come about getting the capital costs, operational costs, and penalty costs separately. The procedure for the GA is much like the standard GA procedure. We start with the initial population. we then perform a selection based on our fitness values, how we calculate the costs. So a lower cost solution would be a higher fitness solution. We perform some genetic operations to alter the networks. We check if constraints are met. If they are met, we can evaluate the solutions. If they aren't met, we would need to add certain equipment and penalties to the system. We then evaluate our solution's fitnesses against a termination condition. And if we meet the termination condition, we stop and we get our final solution. Otherwise, the process repeats. Now, for each of those sections, the initial population is formed by the minimum spanning tree for the given set of nodes, where the minimum spanning tree is just the minimum distance to connect a set of nodes. It's a very simple approach. To make sure that our set of initial population isn't all consisting of the same minimum spanning tree, we perform some random reformations until we are satisfied that the initial population is diversified enough. Next, we perform a stochastic tournament selection, where, of course, it is based on our total costs. So, as I said earlier, we have minimum cost refers to a higher fitness, where we'd have a large population, our entire population, would group it into smaller groups, say a set of 5 groups or more. We then select the best out of those groups and then reform our new population based on those best solutions. So what this method allows us to do is that it is somewhat elitist in that better solutions or the best solution will survive and better solutions are more likely to survive, but you can still get poorer solutions. This allows the system to remain diverse enough. Otherwise, it will converge on a solution too quickly, so it will converge prematurely, we say. Now, the operations themselves consist of 3 main aspects. They consist of Steiner points, which are a centralized point in a triangle. They consist of standalone power systems, so taking a customer off the network and supplying them via their own power system. And lastly, reconfiguration, which is essentially just deleting one edge and supplying that customer via another edge on the network. And these are just indicated, the different approaches in which we can apply these 3 methods are indicated through figures A through F. Cool. So the constraints that we've applied to the model, the first 2 are just some traditional constraints that are always apparent, and they are the voltage deviation limit. So we say the voltage at each of the customers can't be below, say, plus or minus 7% of the per unit voltage. And the system must be radial. So again, since we're looking at rural areas, the networks should be radial for a minimum cost perspective, and as that is the objective in which we're optimizing, it makes sense that we would want a radial network. Additionally, we also look at geographical weights. So just to provide a precursor, in Western Australia in particular, there is a lot of environmental diversity. It's referred to as an environmental hotspot in a lot of areas. What this means is that Western Power can't construct their network wherever they like, essentially. So they will incur a cost if they have to remove vegetation, or if they are passing through an Aboriginal heritage site, or if they're passing through certain properties, land properties. So the way in which we calculate these geographical weights, these extra costs, are based on a grid system. So we construct a grid, just a n by n grid, and at each of the grid points we calculate the cost based on whether or not they are within a polygon, where these polygons represent those weights we considered earlier, the environmental weights, Aboriginal heritage sites, and land subdivisions. We can then sum the weights at each of the grid points and then divide by the number of grid points to get a multiplying factor to our cost. Okay. So after we've taken into account these constraints, we then applied it to this particular network in the rural areas of Western Australia. In particular, this is the Haydn network. Now the network consists of around 316 distribution transformers and approximately the same number of customers. The blue customers that you see are the three-phase customers, whereas the red indicate the single phase. As you can see as well, the area in which we are optimizing is quite large. So even though we only have 300 customers, the area itself is 130 kilometers on the x-axis and another 70 or so kilometers on the y-axis, 90 kilometers. So the area is very large for a very small number of customers. When we apply the algorithm, the GAO, to this network, we find that the cost reduction is around 11%, which is quite substantial considering the network itself is very costly. So if you're saving 11% of a very high number, that's still a substantial reduction. And it also shows that we can actually improve over the existing network architecture, which is expected because the original network could not possibly take into account all future node locations. Now, we go beyond our algorithm, which we apply with the GA, by including those standalone power systems. And when we include the standalone power systems, we find that the reduction further improves to approximately 20%. So what this shows is that the standalone power systems can improve the optimization of the network beyond what is capable solely by the network itself. So in terms of the results, we found if the existing network is 835 units, the optimal network with no SPS drops down to 746, and the optimized network with SPS drops down to 670. So there are substantial drops for each optimization step we just showed. And in the top figure, we just show how the best solutions differ over time. So our network doesn't get any better after around 350 iterations. We also made a number of assumptions for doing this optimization. We locked the three-phase line. So if you're unaware, the power system in these areas will have a three-phase line as the backbone with single-phase spurs branching off of it. We locked the three-phase line based on constraints given by Western Power stating that they are unlikely to modify the three-phase line due to the fact that it is essentially parallel to roads. Additionally, we didn't have a variable discount rate. We had a fixed discount rate. And since this optimization is performed over a period of time, an investment period, it would make more sense to include a variable discount rate. But as we are not privy to that information, we have just stuck with a fixed discount rate for the time being. Additionally, the outage costs have not yet been incorporated. So as I mentioned near the start, the operational costs consist of both the power losses in the line as well as the outage costs, where the outage costs are refer to the loss, not the losses of electricity, but the losses of electricity to supplying a customer. So if you have an outage on a line, a customer won't be supplied electricity for a certain amount of time, and the network operator, such as Western Power, will incur a cost due to that. Additionally, there's no decommissioning cost. So if we are going to rebuild the network, we not only need to rebuild, if we are going to rebuild the network separately, we're not only going to construct the new network, we also have to take the old network down as a safety precaution. So that cost of taking the network down has not been factored in. And lastly, we need a transition plan or a multi-stage planning approach to make the optimization more practical. Because every year you have to consider the fact that a network operator such as Western Power will only have a limited amount of funding to do these projects, so they'll do incremental changes to the network. It won't just be old network to the new network, it will be old network slightly change, slightly change, slightly change until you get to that final optimization. Now, moving on to the second method in which we performed the optimization of the power distribution network, we considered standalone power systems as a result of the outputs from the previous model, which showed that just including standalone power systems improved the results from the network optimization by about 9%. Additionally, Western Power is trialing standalone power systems throughout the state, throughout the rural areas of the state. And the fact that in the beginning of 2016, last year, there were bushfires in Varuna and Yarloop, which damaged or destroyed many properties as well as the power network itself. So even though people got to return to their houses, they had no electricity because the power networks were destroyed. So we want to investigate if instead of the power networks being destroyed, if they have a standalone power system, is that a more optimal solution to bushfire risk areas? So we created a methodology to solve or to identify standalone power systems to address the bushfire risk areas. And this was applied at the time that these bushfire risk areas were occurring. So the algorithm itself, while it was simple, the purpose was just to get it to work and to see what the preliminary results were. So I'll provide a more thorough overview of the algorithm in just a moment. I just want to go through what some of the results indicate so far. So we applied it for 3 areas of the network in these bushfire affected areas. What we have, and what the figures will show, is that the sections which are grayed out are our networks which will be taken off and given or supplied by our standalone power systems, where the triangles represent our customers and the points or the dots represent the poles themselves, so the physical assets. The green indicates just assets which Western Power is planning to replace in the next few years. So ideally, you would have the network section will be grayed out with green assets on top of it. So for this particular network, we do find a few possible SBS solutions, but there aren't many collaborations with the network investment plan, with the works that you're planning to change. So while ideally you would have these customers on standalone power systems, if Western Power is not planning to make these changes in the next few years, they're unlikely to perform these changes. Similarly, we have more sections of the network which can be placed onto standalone power systems, but aren't also in the investment plan, so they're not as ideal. Here we investigate another area where this particular solution is an example of a good standalone power system candidate. We identify that taking that section off is cost effective, and the assets that will be taken off are all needing to be replaced in the next few years anyway. So that is an ideal SBS candidate that we've identified. Similarly, we found other areas other standalone power systems which were not as viable. Just these few scenarios. However, in terms of the outcomes for these particular networks, just using this simple standalone power system approach, we found that yes, there were a number of standalone power system candidates, and that the cost reduction, and this is just in units, so you can consider this to be the cost of 1 kilometre of single phase line. So the reduction for each of these scenarios was 12.7, 4.56 and 2.9, which indicate 12.7 kilometres of a single phase line, for example. Now, standalone power systems do exist, which is nice to identify for the practical scenario. However, we do have a few issues that we need to address before this becomes a more applicable algorithm. Firstly, operational costs were not yet modelled, so we were just looking at capital costs for these projects. But considering the fact that standalone power systems would be an investment for a long period of time, it obviously makes sense that you would include the operational costs in this modelling. Additionally, while our results do provide nice visual outputs, we would like a more financial model, so a more detailed description of what the costs will be, rather than just visually displaying the output. Now, to do this, we spent the next few months establishing a more concrete and more precise algorithm. And the model for this algorithm is based on two aspects. It's based on network formation and the customer loads. So we start with making database queries from Western Power's database. We take information such as the poles, transformers, meters, switches, protection devices, and power quality devices. We then conform the network itself via extracting the pole and transformer IDs and location, as well as the bay IDs and location, and using this information to construct the network in a similar sense to what is shown here. Now, we can also establish what the sizes of the standalone power systems would be based on the equipment mapping, so mapping between a meter itself and a transformer, and based on consumption data. So as an example to describe what I'm referring to, if the transformer was 123 and it had 3 meters attached to this transformer, each meter would have a usage, in this case 12, 35.3, and 1.2. And we can size our standalone power systems based on those meter usages. And these SPS sizes will all be referred to the transformer ID. Okay, so now the actual algorithm for doing the path tracing is a bit complicated, but to provide a dumbed down version, we get our input data, so that's the network formation and the customer standalone power system loads we just referred to. We identify the edge of network customers. So just indicated here, we're identifying the edge of network customers, and we trace upstream until we reach another intersection or another transformer. Now, for each of these sections that we are tracing upstream, we're considering, is this section of the network cheaper than rebuilding the network? So can we remove the network and replace it with a standalone power system, or do we need to just leave it as it is? So while this method identifies all the individual edges, edge of network opportunities, so all the customers on the edge of the network, we can correctly identify if they should be standalone power systems, it can miss groups of standalone power systems. So as it is only considering one at a time, it can miss scenarios where you have multiple very close together and then a long stretch afterwards. So we applied this model to all throughout Western Power's rural networks. It's composed of around 200,000 customers. But for this presentation, I'm just going to describe the results for one of them, one of the particular feeders. So this feeder refers to or supplies power to 191 customers. The loads on this feeder account from 0 to 50 kilowatt hours per day on average. And the length of the network is 580 kilometers in a 60 by 80 kilometer area. So again, it is quite a large area with a low customer density, which is the ideal locations for standalone power systems and other distributed generation. And here's just the network itself, where the blue triangles just indicate the customers, whereas the red circles indicate customers which have a usage that is too high for SPS. So when we apply the algorithm, we find a lot of the network actually goes or is removed, where the network we saw before, which we displayed through the animation, is just in that green circle there. So there are large amounts of the network that have now been taken off due to standalone power systems. So when we consider the results, we find that if we're not using any other constraints, roughly half of the customers on the network can be replaced via standalone power systems. And this results in a reduction in the network assets by around 40% So as Western Power is a poles and wires business essentially, reducing part of their network by 40% is a significant change to their business model. It's something they would have to address. Now, to make the results a bit more practical, we added a few more constraints. So we indicated that the standalone power system solutions have to at least be 20% better than the cost of the rebuilding the network. And the age of the assets themselves have to, on average, be greater than 40 years. So we are, again, targeting the older assets, which will be placed in the next few years anyway. Now, I just want to indicate, these solutions that we get won't be applicable to the entire network itself. So Western Power is not going to reduce their solutions by 28%, for example. It is just that for this particular area which we chose, the reduction would be around 28% if you replaced all the viable candidates with standalone power systems. Okay, so in conclusion, from this model, we find that the SPS model has identified many standalone power system opportunities, and some of these opportunities provide significant benefits financially to Western Power and possibly to the customer as well. In the future, we have to address a few present issues, such as the data quality issues. So you might be able to see in the bottom right, there is an extended grey section at the top. That extended grey section doesn't connect to a customer, which is likely a data quality issue. So there likely is a customer at the end of that network. It's just that our query, our data extraction didn't detect that network, that particular customer. Additionally, we are going to consider risk and reliability. So far we have just focused on the optimization of cost, but we also need to consider what the risk is. So what is the bushfire risk? What is the risk towards the environment or towards electrocution or the safety of personnel? And reliability in the sense that, of course, these areas need to be, will need to meet certain regulations. So you can't optimize with regards to cost, but ignore the fact that the reliability might be potentially lowering. Additionally, we are investigating some clustering mechanics to expand the GA to consider microgrids. And we're also shifting focus of the genetic algorithm towards the application of the SPS and the microgrids. So just again, some assumptions we've made for the model. We based it on a 50-year investment period. We used a fixed discount rate again. The cost parameters were assumed are correct, but they may not be. They may change over time. Of course, the cost of renewable technology is likely to decrease, so that is something we should model in the future. Again, the outages have not yet been incorporated. The reason the outages haven't yet been incorporated is just because since this technology is only in trial programs, it's unsure what the outage rates will be. And again, similarly as the previous method, the decommissioning costs were not included. The last thing we want to include for the SPS model, though, is the geographical constraints. So while we did consider it for the GA model, we haven't considered it yet for this standalone power system model. So just in summary, we provided two methods of optimizing the power distribution network. The first method looked at altering the topology of the network through using a genetic algorithm. We found that the reduction in costs was around 20% for a particular application. And the second approach, we applied standalone power system methodology throughout Western Power's rural network. And we found that in many cases, standalone power systems do provide a reduction in cost. So you can read a little bit about the work we've done just on this website. And I'd just like to make a few acknowledgements to Patrick Doran-Wu, Brad Smith, Jai Thomas, and Matthew Webb from Western Power for providing assistance throughout the project. Okay, any questions? Cool.
Very quick question.
Okay, yeah.
I have a quick question about the SPS. Is that only completely off-grid, or you can connect it back to the main grid?
No, so the standalone power systems are completely off-grid. The benefit you're getting out of the standalone power system is that you are removing the lengthy line. So as I was saying earlier, these networks in rural areas are very low density for customers. So there is extensive capital infrastructure to supply power to a customer. What we are saying is that if you remove some of that infrastructure and just supply that customer by themselves, the cost will significantly be lower. Yeah. So they're islanded, completely islanded.
When you design the SPS, is that the capacity of the SPS is completely depend on how many customers you have?
Yes, it's based on existing customers.
Right now, so you don't have. When there is a new customer come in, you need to upgrade your facility.
Yep. So that's another thing you need to consider. You don't want to take a customer off the network, and then a few years later, there's another customer who needs to also be connected. So it would make more sense to supply via the network as well. But what you have to consider is that, again, we're looking at rural areas. So since we're looking at rural areas, most of these towns or most of these farms aren't expanding, or they're expanding very slowly. So in which case, it's unlikely that that's going to be a significant issue. No worries.